Good afternoon. My name is Malik Sproul, and I am one of the senior software engineers at GreenPace. In this presentation, we'll break down our updated GreenPace Security Policy Guide, turning the best practices we've integrated into structured, standardized approaches to security infrastructure. This presentation will outline the popular defense in depth strategy to safeguard our company as well as our users. By leveraging a multi-layered approach, we will now incorporate various tools and policies to protect everything from physical security to application security and beyond. Our coding standards will help mitigate existing vulnerabilities while proactively preventing future risks. In other words, more peace of mind for all of us. This threats matrix categorizes key security risks by their likelihood and priority, aligning them with specific coding standards. High priority areas include type safety, value safety, string manipulation, SQL injection, and memory management, as these present significant security threats if not properly addressed. Exception handling and documentation are classified as likely concerns, while assertions and hard-coded values are considered lower priorities. Automated tools like SonarQube can assist in enforcing these standards, ensuring code quality and security compliance across the development process. In front of you, these are the 10 core security principles and illustrates how some coding standards can adhere to multiple principles. One key principle outlined in the table is validate input data, which is supported by standards such as STD 001. This standard ensures that all input is properly checked and sanitized before being processed, helping to prevent vulnerabilities like buffer overflows and SQL injection attacks. By enforcing strict validation rules, developers can reduce the risk of malicious data being used to exploit the system. Another crucial principle is adhere to the principle of least privilege, backed by STD 010, which ensures that users and processes are granted only the minimum permissions necessary to perform their functions. This limits potential damage from security breaches by reducing the attack surface available to malicious actors. As you can see here are the same coding standards ranked from highest or immediate priority to reviewing priority. These rules have also been evaluated by their vulnerability criticality, and we have the two charts to refer to on the right side of the standards list. Some of you might notice similar rules involving use of parameterized queries, proper string handling, and memory deallocation. Not doing so, this could expose a system to unknown issues, SQL injections, memory leaks, and the list goes on. Encryption policies ensure data protection across three key states: at rest, in flight, and in use. Data at rest is encrypted using strong algorithms to prevent unauthorized access, aligning with the principle of least privilege by restricting decryption to authorized users. In flight, encryption safeguards data transmitted over networks through protocols like TLS, SSL, preventing interception and ensuring data integrity between systems. Lastly, in-use encryption secures actively processed data in memory, implementing multiple layers of security to mitigate risks from potential breaches or unauthorized access during runtime. AAA is a security framework that stands for each of the policies you see here: authentication, authorization, and accounting. Authentication policies ensure that users are who they claim to be through methods like password-based authentication, multi-factor authentication, and public key infrastructure. These measures enhance security by requiring multiple credentials or cryptographic keys to verify identity. Authorization policies, on the other hand, dictate what authenticated users are allowed to do, utilizing role-based access control to assign permissions based on roles. Additionally, time-based restrictions can enforce limited access to resources based on specific time frames. Lastly, accounting policies focus on tracking user activity, such as session monitoring, which logs login times and interactions. Billing, cost allocation, and compliance reporting also fall under accounting, ensuring resource usage is recorded and policy adherence is maintained. GreenPace adhering to these policies would be critical for ensuring our security infrastructure is defensive against malicious intent. We'll be showcasing 4 tests consisting of positive and negative tests for data type testing for the next 4 slides. This test utilizes Google test and verifies that calling erase begin end on a vector collection successfully removes all elements, leaving it empty. It first ensures that the collection starts empty, then adds 2 elements, and finally erases them while asserting that the collection is empty afterward. This is important to test because it confirms that the erase function behaves as expected, preventing potential memory leaks or expected behavior in applications that rely on clearing collections. This test verifies that calling reserve on a vector collection increases its capacity without affecting its size. It first checks that the collection starts empty with 0 capacity, then calls reserve and asserts that the capacity is updated while the size remains unchanged. This is important because it ensures that reserve works correctly and only pre-allocates memory without adding elements as intended, which is crucial for optimizing performance in dynamic array usage. Again, this is another test that uses Google test and ensures that calling at on a vector with an outer range index correctly throws a standard outer range exception. It first verifies that the collection is initially empty, then adds 1 element and checks that accessing an invalid index, both above and below the valid range, triggers the expected exception. This is crucial for validating safe access to elements and preventing undefined behavior in cases of invalid indexing. This is the last test showcase. This test checks whether swapping a vector with itself has any unintended side effects. The test first ensures the collection is empty, then adds 1 element, verifies its size, and swaps the collection with itself. Finally, it confirms that the size remains unchanged after the swap. The test passing indicates that swapping a vector with itself is safe and does not modify its state, preventing unintended errors. A key advantage of the DevSecOps approach is that automation integrates seamlessly into the development workflow instead of being an afterthought. Various automation tools are available with diverse functionalities that enable efficient and effective security analysis and testing, allowing them to become a natural part of the iterative development cycle. Let's view a number of these tools now. The DevSecOps pipeline integrates security into the development lifecycle, ensuring continuous assessment, testing, and monitoring. Pre-production involves planning with tools like Open Web Application Security Protocol and SonarQube for vulnerability scanning, designing secure applications, building with automation via Jenkins, and verifying with Valgrind for debugging. In production, security is maintained through monitoring with Slack, intrusion detection using Snort, and real-time incident response with Splunk. The cycle is completed with stabilization efforts, including patching, audits, and recovery to maintain a secure and resilient system. This integrative effort places our contributions to our security architecture in great standing. Delaying action on security issues can lead to SQL injection attacks, memory leaks, and unsafe string operations, which pose risks such as system crashes, legal costs, and operational slowdowns. Immediate action, including implementing prepared statements, smart pointers, and safe string handling, enhances security, improves system performance, and reduces long-term expenses. Addressing these gaps early helps mitigate vulnerabilities, ensuring efficient memory management and preventing data corruption. Failure to act in time results in increased troubleshooting efforts, slower query execution, and potential downtime, affecting overall system reliability and business longevity. To improve our security and compliance, we here at GreenPace should schedule external audits, follow industry standards, and implement structured security training programs. Expanding security testing to include integration, load, and penetration testing will help identify vulnerabilities proactively. Additionally, enforcing cloud security measures like role-based access control and periodic access reviews will strengthen authorization protocols and mitigate risks. Overall, Adhering to the aforementioned principles and standards, as well as the architectural concepts, that is, defense in depth, and the AAA framework, our security infrastructure will be inevitably much more reinforced. In conclusion, getting hacked isn't just some wordplay from someone making a threat from losing a video game match against you online. Malicious intent such as this can lead to companies, users, and entire global infrastructure being affected if security isn't prioritized. With that said, note that a security mindset should exist in our development, testing, training, and overall planning. And remember, zero trust always.